Welcome. In this video, I'd like to describe how a simple magnifying glass works, and also introduce the concept of angular magnification. Before we can talk about angular magnification, I want to do a quick review of how we measure angles in physics. Now, the picture, you see a circle, a radius r. Now suppose we travel along that circle a distance s. S we would call the arc length. You're traveling around the circle, you move a distance s. You want to describe how far you have traveled. Well, on that picture, you could say I went so many millimeters or so many centimeters. But unless the person knows how big the circle is, they don't know if you traveled a little or a lot. So a way to describe how far you traveled that includes the size of the circle is tell how far you traveled in terms of how many radii. We introduce the angle theta equal to the arc length divided by the radius. We call the unit radians. For instance, if the radius was 2 centimeters and you traveled 2 centimeters, you'd say I traveled 1 radius. If the radius is 2 centimeters and you traveled 4 centimeters, you say, well, I traveled 2 radii. So we introduce the unit, we call it radian. It's the distance, that arc length divided by the radius. Now notice, although we call the unit radians, if s was in centimeter and r was in centimeter, the unit would have canceled out. So it's kind of a non-unit. It's the number of radii, we call it radians. Now, if you traveled the entire circle, you made 1 revolution around the circle, the distance you would travel would be the circumference, 2 pi r. If you divide that by r, you'd say I traveled 2 pi radians. So 2 pi radians equal 1 circle. So there it is, 1 revolution. You might say 360 degrees. In physics, it's more helpful to say 2 pi radians. Okay, so that's review of the radian, or I've abbreviated as rad. Now, I want to talk about something called the small angle approximation. It's going to be very helpful when we describe angular magnification. So I've got a radius. It's much bigger than the arc length s. There's the angle theta. What is the small angle approximation? Well, notice that s is a part of a curve. But if the angle is small enough, you can approximate that as a straight line distance. See there? It looks like on the right-hand side a right triangle. So you see that vertical side of the triangle is going to be ever so slightly shorter than the arc length because it doesn't have any curve. It's going a straight, the straight distance between the 2 points. You can see that's not going to work for a big angle. But for a small angle, that's going to be really, really close. So that's a very useful approximation. For light entering the eye, it's going to enter at a small angle. So the small angle approximation is going to work for the problems we're treating. Okay, so in that small angle, theta will be that straight line divided by r. Very close to the actual S divided by r. All right, so here's the first case. The angle of view. So you want to look at something as close as possible because you want to see it as large as possible. So there's the object, the red arrow, h sub o. And if you want to see it as close as possible, that's going to be 25 centimeter. Remember from the video talking about vision correction, you can't really focus if something is closer than 25 centimeter. Not normally. So the best you can hope for is bring that object to 25 centimeter. Then the angle of view, we can draw those rays going to the center of the lens. You see that forms the real inverted image on the retina. That angle of view, call it theta of the light entering the eye, or of the object, h sub o divided by 25. Now, I'm not including the units in every equation. It makes it more complicated. But of course, for this to work, we're assuming the 25 is centimeter, that HO better be measured in centimeter. If you measure it in millimeter, you better convert it to centimeter. Now, what if you want to look at something very small? It's still too small. How can I make it bigger? So I'll bring it closer. But if you bring it closer, you can't focus. But then you remember, if I use a converging lens, I bring the object closer, I make a virtual image further away. Now, the virtual image is bigger, it's further away, therefore, the same angle of view from the virtual image as from the object. Only now, because of the lens, the object is closer than 25 centimeter. So here you see what's going on. By using this converging lens, remember you have to use a converging lens if you want to bring the object closer than the focal and make that virtual image further away. By using the converging lens, you're looking at something that appears larger because it is now closer. The object's closer, but the image, in order to focus on it, is further away. Again, you can go back and review the video on vision correction, or review the video on image formation by lenses to see how it works. What's different now is, rather than talking about the size of the image, the size of the object, we're concerned about the angle it makes on the eye. As that angle gets bigger, you see that image is going to be bigger on the retina. Now, if that converging lens is very close to the eye, then the distance from the eye to the object is going to be DO, the same as the distance from the object to the lens. So the angle with the lens is HO, the size of the object, over DO. You see the little triangle there. We're still assuming small angle approximation. So we have two angles. The angle of the eye only, where you have the object at 25 centimeter. The angle when you use the lens. The lens helps you. It's like the far-sighted correction. You bring the object closer than you're able to focus, but the image is further away where you can focus on it. So let's consider what we call angular magnification. Now I'm using a capital M with a subscript theta to mean it's angular magnification. Now, different books whatever, may use different terminology. This is what I'm using here. Magnification, subscript theta, to indicate its angular magnification. It's the ratio of theta using the lens divided by theta with the eye only. And of course, we're saying what is the best case. With a lens, it's HO over DO divided by the eye, HO over 25. The HO cancels out of that equation, and you're left with 25 over DO, the image distance. You say, wow, I guess there's no limit to how close I can bring it. Well, yeah, the value of DO is going to determine where the image is and whether you can focus on it or not. Suppose you had a job where you had to, or whatever, some vocation where you had to look at things magnified for long periods of time. Maybe you're a jeweler. You have a little magnifying glass, got a loop you place on the eye to look at jewelry up close. Or maybe you're doing microscopy. You look through the eyepiece for a long period of time. Maybe astronomy. You're looking through a telescope, the eyepiece, for long periods of time. It would be convenient if you could look at something magnified without straining your eyes. So what's the best place to put the image? Remember, you're looking at a virtual image. The best place for the virtual image is you can look at it without straining your eyes. In particular, you can look at it with relaxed vision. Well, to have relaxed vision, you want to put the image at infinity. You say, oh, it's going to be too small. No. As it gets further away, it gets bigger, so you have the same angle of view. But as it gets further away, the rays of light coming from that image will come parallel. The parallel rays, and really, we say infinity, if you remember the vision correction, something much greater than a meter away. So you get the thing far enough away, you can look at it with relaxed viewing. Okay, here's the equation for the locations. What value of d sub O will put the image at infinity? Well, let's substitute infinity for di. You look at the equation, it should start to look kind of familiar. 1 over infinity is 0. The solution to the equation, do equals f. So, for relaxed viewing, remember, relaxed viewing is as though the image was far away. What that means, the rays come in parallel. The eye can focus without having to squeeze that lens. So m sub theta, the angular magnification, is 25 over f. Because when do equals f, the image is at infinity. Now, maybe you've seen this before, maybe you haven't. But this particular equation is something you should be familiar with. This defines what is called the lens times magnification. If you look at an eyepiece of a microscope and it says 10x or 5x, or you go to buy a magnifying glass and it says 2x or 5x, what is that 2x or 5x? It's that formula right there. 25 divided by the focal length of that lens. Here's a question to think about. Can any converging lens be used as a magnifying glass? Seems like we should be able to take any converging lens, use it as a magnifying glass. Well, not really. What if f is greater than 25 centimeter? Remember this equation, we're assuming everything is centimeter to Makes sense. The 25 is centimeter, the f is centimeter. If f is greater than 25 centimeter, the angular magnification less than 1. You don't want to look at something smaller than you can see with your naked eye. So for a converging lens to be a magnifying glass, the focal length has to be smaller than 25 centimeter. And you see, the shorter the focal length, the bigger the magnification. We tend to think, oh, a lens with a big focal length is powerful. No, it's the opposite. The shorter the focal length, the more powerful the lens. Remember the diopter, 1 over the focal length in meters. This magnification, 25 over the focal length in centimeter. The times magnification. Okay, so what is going on? Okay, here's a magnifying glass. What you want to do is hold that magnifying glass close to your eye and put the object at the focal point. There's the ray diagram. You see, there's the capital F, the focal point. The rays going to the right, you don't care. You care about the rays moving to the left. They pass through the lens, they come to your eye. So what happens? As the rays leave the focal point, go to the lens, they will emerge parallel. Parallel rays into your eye. It's as though you're looking at something at great distance. Relaxed viewing. It's like staring at the clouds. You don't strain your eyes to look at the clouds. The key to the magnification, the smaller the focal length, lowercase f, the closer and closer that thing gets to the lens. You put the lens close to your eye, the larger and larger that angle where the image enters your eye. So let's do a quick example. That magnifying glass right there on the right. Suppose the focal length of that magnifying glass is 100 millimeter. Yeah, that sounds like a pretty decent number, 100 millimeter. What would that be in diopters? Well, diopter, we have to convert the focal length to meter. Now, milli is 10 to the minus 3. So 100 millimeter, 100 times 10 to the minus 3, that's 0.1 meter. So the power in diopters, 1 over the focal in meters, 1 over 0.1 meters, 100 millimeter, 0.1 meter, 10 diopters. So that lens is 10 diopters. So that sounds pretty good, because if I get a prescription for contact lenses or glasses, 10 diopters would be pretty big. Usually they're going to be somewhat smaller than 10 diopter. Now, it doesn't have to be, but 10 diopters is a decent size number. But then you wonder, what's the magnification? Well, that equation, 25 over f, we have to convert f to centimeter. 10 millimeter equals 1 centimeter. Therefore, 100 millimeter is 10 centimeters. So the angular magnification, 25 over f in centimeter, 25 over 10, 2.5x. You see that, and you say, wow, 2.5x, that doesn't look very powerful. You're used to, like in a microscope, telescope, 5x, 10x, whatever. 2.5x, that's a useful magnifying glass. But you see in context how it compares to the 10 diopter, the 100 millimeter. It's the same lens every time, but 3 different ways to describe it. And you come across these in different contexts. In photography and optics, you typically describe lens millimeter. For optometry and vision correction, use diopter. For an eyepiece on a microscope, telescope, magnifying glass, you typically will see the times magnification. That's the end of the video, and I thank you for watching, listening all the way to the end.